All right, let's get this deep dive started. Today, it's all about time series modeling and how we can use it to, kind of peek into the future a little bit.
Yeah, predicting what's coming next. And it's not just some futuristic fantasy.
Right. It's used in so many
Oh,
areas.
yeah, everything.
Finance, healthcare, even just like the weather.
Absolutely, yeah. Time series modeling, it's all about looking at data that's collected over time and trying to find those patterns to predict future trends.
Exactly. And the challenge, I guess, is that the amount of data we have keeps growing like exponentially,
It
right?
really is, yeah. Think huge data sets.
So how do you even build models that can handle all that?
Right, it's tough. The traditional approaches, like transformers or LSTMs,
Yeah, I've heard of those.
they kind of struggle when you get to those really massive data sets.
Like they can't keep up or something.
Yeah, exactly. It's like they get overloaded.
Makes sense. But okay, that's where BlackGoose comes in, right? This new model we're talking about,
Yeah, this is where it gets interesting.
because it uses a different approach.
Well, it actually brings back something that people thought was a bit outdated.
Oh, what's that?
RNNs, recurrent neural networks.
RNNs, seriously.
Yeah, a lot of people thought they'd been surpassed, but BlackGoose, it uses a special kind of RNN called RWKV-7.
Okay, so it's like a comeback tour for RNNs.
Ha, kind of. And it's all thanks to these two awesome components that RWKV-7 has. They're called time mix and channel mix.
Time mix, channel mix. I'm picturing like a fancy DJ setup for data.
Hmm.
But seriously, what do those actually do?
Okay, so imagine you're trying to predict, I don't know, let's say the stock market.
High stakes.
Right. Time mix, it looks back at the stock prices over the past, however long.
Okay.
But it's not just averaging things out. It
Oh.
figures out how much importance to give each day's.
Oh, so like maybe yesterday's price is way more important than last month's price.
Exactly. And time mix, it learns that all on its own.
Wow, that's pretty smart.
Yeah, it's learning those complex dependencies over time.
Okay, makes sense. But what about channel mix? Where does that fit in?
So channel mix, it's like imagine you're also looking at other factors that might affect the stock market.
Like economic news or something?
Exactly. Interest rates, company earnings, all sorts of things.
Okay,
Channel mix helps figure out which of those factors are most important for predicting stock price.
got it. So it's like filtering out the noise and finding the signal.
Yes, way to put it.
Okay, so we've got time mix and channel mix working together.
Right.
But how does this all actually happen inside RWKV-7? Like, what's the magic formula?
Well, it's all down to this thing called the state update rule. It's kind of technical, but essentially it's like the engine of the whole process.
Okay, I'm listening.
It takes the new information coming in, considers the past thanks to time mix, then channel mix refines it all.
And boom, you get a prediction?
Well, not quite that simple, but it updates the model's understanding of the data.
Okay, I think I'm following along. But I've also heard about these deep equilibrium models. Yeah, those honestly, they sound kind of intimidating.
I know, in a mouthful, right? But the idea is actually really cool.
Lay it on me.
So imagine you're trying to solve a really complicated puzzle.
Okay, I'm with you.
Usually you have to keep thinking about all the pieces going back and forth.
Right?
DQs are like, imagine you could instantly see the whole solution without having to go through all those steps.
Whoa, like you just know it.
Exactly. It's like reaching this state of perfect balance where everything just clicks into place.
Okay, that makes more sense than some crazy equation. Haha.
Right. And that's how Rimmer can handle those huge data sets so efficiently.
So it's both powerful and efficient. That's impressive.
It really is.
I'm already intrigued, and we haven't even gotten to the results yet.
Oh, yeah. The results are where things get really exciting.
All right, well, let's take a quick pause and then come back and dive into those because I'm dying to know how Black Goose Rhymer actually stacks up against the competition.
Sounds good. All right. So where were we? Oh, yeah. We were about to unpack those results and see how BlackGoose Rimmer measures up.
Right. I mean, we've talked about all the cool stuff under the hood.
Yeah. The time mix, the channel mix, all that.
But how did it actually perform? Like in the real world, not just some theory.
Okay, so they put Reimer's paces, tested it against a state-of-the-art model called Timer, which uses transformers.
Okay, the big leagues.
Yeah, and they used 4 different data sets, ELC, ETEATS traffic, and weather data.
Wow, so a good mix of different stuff.
Right, they wanted to see how it would handle different types of time series data.
And drum roll, please. What happened?
Reimer was 23 times smaller than Timer.
What? Smaller?
Yeah, but it either outperformed or matched Timer across all the data sets.
Hold on. Smaller and better? How is that even possible?
It is pretty amazing, right? It shows you don't always need to go bigger and bigger to get better results.
So, what were some of the specific areas where Rhymer really shined?
Well, one thing that stood out was its performance on this metric called MAPE, mean absolute percentage error.
MAPE. Okay, break that down for me.
Basically, it tells you how far off the predictions are, on average, as a percentage.
Okay, got it.
And Raymer had a lower MAPE on certain data sets than Timer, its predictions were closer to the actual values.
So more accurate, basically.
Exactly. And that's a big deal because even small errors can have significant consequences in real-world applications.
Right, like if you're predicting energy demand and you're off by a few percent,
Oh, it could lead to blackouts or wasted resources.
yeah, not good.
But Reimer's lower MAPE suggests it's better at handling those tricky outliers that can skew the predictions.
So it's more robust, more reliable.
Yeah, that's a good way to put it.
Okay, so lower MAPE, that's one win for Reimer. What else impressed you?
Another thing was its higher R-squared values.
R squared, that sounds familiar.
It basically tells you how well the model captures the overall patterns and trends in the data.
Okay, so if R squared is high, that means the model is doing a good job of following the data.
Exactly, and Reimer consistently had higher R-squared values than Timer.
Wow, so it's not just about being accurate, but understanding the bigger picture, the long-term trends.
Exactly, which is super important for things like financial forecasting or predicting climate change impacts.
Makes sense. Okay, so Reimer is smaller, more accurate, and better at capturing those long-term trends.
Pretty impressive, right?
Yeah, color be pressed. But I'm curious, how did they actually build this thing? Like, what tools and hardware did they use to make all this magic happen?
Okay, so they use these things called Triton operators. They're like specialized tools for building deep learning models.
Okay.
It gives them really fine-grained control over the calculations, which is super important for something as complex as RWKV-7.
So it's like having the right tools for the job, not just trying to hammer in a screw.
Exactly. And they developed and trained Reimer on a Linux RCM platform.
RSCM, is that like the other GPU platform?
Yeah, it's not as well known as NVIDIA, but it's becoming increasingly popular, especially in research.
Why is that?
Well, it's often more cost-effective, and it gives developers more flexibility and control.
The indie darling of the GPU world.
Yeah, kinda. And because of those Trident operators, Reimer can actually run on different types of hardware.
Oh, really? Like what?
NVIDIA GPUs, even CPUs.
Wow, so it's not limited to just one platform.
Right, that makes it super versatile and accessible to more people.
Okay, so we've got the how it works, we've got the how well it works, but what about the what's next?
Yeah, where do they go from here?
Exactly. What are the researchers hoping to do with BlackGoose Reimer in the future?
Okay, so one thing they're really excited about is enhancing its ability to handle even longer contexts.
Longer context, you mean like looking back even further in time?
Exactly. Remember how time mix looks at past data? They want to make it look back even further, potentially years or even decades.
Whoa, that's a lot of data.
It is, but it would make Reimer even more powerful for predicting long-term trends and understanding those really complex systems.
Like, I don't know, climate modeling or economic forecasting.
Yeah, those are great examples.
But wouldn't that require like massive amounts of computing power?
It would, and that's where those state chains come in. It's a way of optimizing how Reimer stores and accesses long-term memory so it doesn't get bogged down.
Okay, so longer context, that's one thing. What else? Horizon?
Another really interesting area is exploring something called latent space representation.
Space representations. Okay, you're losing me a little bit.
Haha, it's a bit abstract, but basically it's about finding those hidden patterns and relationships in the data that we might not see just by looking at the surface.
Okay, give me an example.
Imagine you're analyzing thousands of customer reviews for a product.
Okay, I can picture that.
Latent space representations could help you discover that people who use certain words in their reviews, even if they're not directly related to the product's features, tend to have similar opinions.
Oh, so it's like finding those subtle connections that you wouldn't normally pick up on.
Exactly, it's like reading between the lines.
And how does this apply to Reimer?
Well, these latent space representations could make Reimer even more efficient and powerful because it's essentially distilling the data down to its most essential elements.
Okay, so it's like finding the signal in the noise, but on a whole other level.
Yeah, that's a great way to put it.
All right, longer context, latent space representations. I'm sensing a theme here.
What's that?
It seems like they're really trying to push the limits of what Reimer can do, make it even more versatile and insightful.
Yeah, that's a good observation. They're constantly looking for ways to improve it.
And I'm sure they've got even more ideas up their sleeves.
Oh, I'm sure they do. It's a very active area of research.
Well, this has been an incredible journey so far, but I think we need to take a quick break to let all this information sink in.
Sounds good.
We'll be back soon to wrap up this deep dive and talk about what it all means for you, our listeners, out there in the real world. Okay, we're back, and I gotta say, my head is still spinning a little bit from all this BlackGoose Reimer stuff.
Yeah, it's a lot to take in, but that's what makes it so exciting, right?
Right, but before we get lost in the technical details, I think it's important to remember that this isn't just some abstract concept. This has real-world implications.
Oh, absolutely. Time series modeling, it's the foundation of so many things we rely on.
Like what?
Think about predicting financial markets, managing energy grids,
Right, those are big ones.
understanding climate patterns, even personalizing healthcare treatments.
Wow, it really is everywhere.
Yeah, it's woven into the fabric of our lives.
So as we wrap up this deep dive, let's try everything we've learned into some key takeaways for our listeners. Like, what are the big haha moments they should walk away with?
Okay, so first off, I think BlackGoose Rhymer has shown us that RNNs are far from dead.
Yeah, they're making a comeback.
That clever design of RWKV-7 with the time mix and channel mix,
Yeah,
it proves that RNNs can be incredibly powerful and efficient, even beating those transformer models that everyone's been talking about.
right. It's like they found a way to make them work even better.
Exactly. And we also have to give credit to those deep equilibrium models, the DQs.
Those were a bit mind-bending, I have to admit.
They are, but they're also kind of elegant in a way, you know?
Yeah, I get it now. It's like they allow Rimmer to process all that information without getting bogged down.
Yeah, like a super efficient brain.
And that leads to more accurate predictions, faster processing times, ultimately better decisions.
Precisely. And that's why this has the potential to be so impactful across so many different fields.
It's really exciting to think about. Like, imagine using Rambert to predict disease outbreaks weeks or even months in advance,
Oh, yeah, that would be huge.
or to optimize traffic in cities, reduce congestion and pollution,
I mean, the possibilities are endless. And the researchers behind Rhymer, they're not stopping there.
right? They're already looking at those latent space representations.
Yeah, uncovering those hidden patterns in the data.
It's like they're pushing the boundaries of what we thought was possible with time series modeling.
Absolutely. And who knows what other breakthroughs are just around the corner.
Exactly. So to all our listeners out there, stay curious, keep exploring because the world of time series modeling is just getting started.
Well said. And if you want to learn more about BlackGoose Rhymer, we've included links to the original research paper in the show notes.
It's a bit technical, but it's worth checking out if you really want to dive into the details.
Yeah, definitely.
All right, that's all the time we have for today's deep dive.
Thanks for having me. It's been a great conversation.
Thanks for joining us. And to everyone listening, until next time, happy data diving.